Hi and welcome back to a new video. Today is finally the day that we can openly talk about the new Intel Arrow Lake CPUs, its performance and also properties of the CPU that make it quite special and also a challenge when it comes to both testing and also manual overclocking. In the past, for example, we only had P-core, E-core and ring clock, and now we also have D2D clock and NGU clock. Also, the power supply is different versus the previous generation. So there's a lot of things that change that make this CPU especially interesting from a technical perspective, make it very efficient, but also challenging and strange in some aspects. This video is sponsored by the new Thermal Grizzly 1851 contact frame for Intel Arrow Lake CPUs. From our testing, our contact frame can improve the temperatures on an overclocked 285K by up to 6 degrees Celsius if you switch from the normal Intel ILM and up to 4 degrees Celsius if you switch from the reduced load ILM. All feedback from the previous generation was taken into account and the frame is now easier to mount, features an additional isolation layer on the bottom and has new updated stainless steel screws. Check out the frame in the link below. We will straight jump into gaming benchmarks. Today we will compare the 285K versus the 9950X, the 7800X 3D and the previous 14900KS. Usually we start with Cinebench, but this can be challenging. So we start with gaming first because it's actually easier to understand. Intel said during their announcement that the 285K would be very efficient and should be on par with the performance of the previous Intel Raptor Lake generation. In Cyberpunk 2077, the 285K is delivering quite a good performance. It has roughly the same 1% lows as the 14900KS, but is a bit behind on the average FPS. At the same time, the power consumption of the 285K is only half of what we saw with the 14900KS, so we see 117 watt under load. You can always see this in all of my charts in the blue bar. That's always the power consumption. However, if we compare it to the 7800X 3D from AMD, which is still a bit faster, but also consumes still less power. My first impression of the 285K was very positive. It was roughly on par with the 14900KS while consuming half of the power, which was really good. And it also stayed very cold due to the fact that it consumed a lot less power. What you might have missed on this chart is that on the left side you can see the memory configuration. And I was testing all the CPUs with 6000 C30. Except for the Intel Arrow Lake 285K, I was testing that one with 8800 C42, which is, from my perspective, the max that you can realistically do without jumping into Gear 4 memory speed. Well, not memory speed, memory controller speed. So if you would run like 9200 mega transfers on the memory, then the memory controller would jump into Gear 4 and you would lose performance. The reason why I decided to run this very high memory speed is that this scenario from Cyberpunk 2077 is not always the case. So Arrow Lake can also be quite a bit slower. And what I wanted to highlight is that also running very high memory speed might not help it. In Remnant 2, the 285K is performing again quite nice, same as in Cyberpunk, while the power consumption is again very low, with about 80 watt under load. Compared to the 14th gen, that's again about half the power consumption, while the minimum FPS even increased. And in this scenario, it can even beat the 7800X 3D. In Assassin's Creed Mirage, the 285K has absolutely no chance versus the previous 14900KS, even if the 285K is much more efficient and again consumes quite a lot less power. However, the 7800X 3D is still much more efficient and has about 1.3 FPS per watt. That is calculated on the 1% low. Compared to the 9950X, the 285K is again a little bit faster and also consumes less power. If all results would be like the ones I just presented to you, the 285K wouldn't be that bad, even though it's not beating Raptor Lake. But unfortunately, not all results are like that. So if we switch over to Counter-Strike 2, the 285K is incredibly bad and slow. I also added the Ryzen 7600X for the comparison so you can get a better feeling how slow it actually is. And I repeated this testing over 10 times and it always looks exactly like this. I'm not sure why, but the 1% low FPS with the 285K in combination with the RTX 4090 in 1440p are very low. And it's actually getting even worse if I lower the resolution further. So if somebody else is testing at an even lower resolution, which is likely like 720p or 1080p, it's probably even worse. The 285K is very efficient again, but it's 40% behind the 4900KS. And just keep in mind, I tested with 8800 megatransfers on the memory. So if I was testing with like 6000 C30, it might be 50% behind the 4900 KS. I could see the same kind of behavior in Valorant in 4K, which is again a very high FPS shooter, so there might be something to that. The 285K is behind the 9950X, and especially if we compare it to the 7800X 3D or the 4900 KS, it's just like a big gap. 200 FPS less in the 1% low, for my taste, is just too much. The gaming benchmark results seem to be very mixed, and the problem for me is that I'm also only testing a small amount of games, so it's hard for me to get a real impression. Let's say if you would test 50 games, is it more like 80% that are performing bad, or if it's maybe 50-50, I don't know. That's why it's also really important that you check out multiple reviews, watch maybe 10 of them, check people testing different games to get like a bigger impression of how things perform. What I can say though is that I'm positively impressed with how much more efficient the CPU is versus previous gen. So from my perspective, Intel definitely doesn't have the image anymore of being this power hungry, like 100 degrees Celsius all the time chip. That is definitely something for the past. So overall, the CPU should consume between 70 and 100 watt in gaming, which is pretty much the same for the AMD chips. This development of the lower power consumption and lower temperature has multiple reasons. First of all, the CPU is now made by a TSMC, but it also has a completely different architecture, a different way the CPU is built, and a different power supply. That's where the DLVR comes into play, the digital linear voltage regulator. And what it does, and some of its properties, we will just jump into Cinebench. I will show it at the system. We are just running Cinebench straight away and look at what the CPU does. What you will first notice is that the order in hardware info looks a little bit strange. So we have 2 P cores, then we have 8 E cores, 4 P cores, 8 E cores again, and then 2 P cores on the bottom. You see that the P cores are clocking between 5.4 and 5.3 gigahertz. I'm just going to repeat it. And you will see that this is caused by the thermal velocity boost. Once the P core reaches 70 degrees Celsius or above 70 degrees Celsius, it clocks down from 5.4 to 5.3. So that's what's happening right here. And the E cores are clocking stock at about 4.6 gigahertz. If we check in CPU-C, you will first find the 8 P cores and then followed by the 16 E cores. The reason for this, at a first look, confusing order is that hardware info, for example, is replicating how the CPU is physically built, because the chip exactly looks like that. So you have P cores on top, E cores again, P cores, E cores, P cores, while, for example, for Alder Lake, you only had P cores on top and E cores on the bottom. And that's why they went for this kind of order. That can be confusing, and it's important to know that also the task manager has the same kind of order as hardware info. So if you want to assign a specific task to a specific core, you have to be really careful not to mistake an E core for a P core, for example. Back to Cinebench, keep in mind that we lose a bit of performance because of hardware info running in the background. The temperatures, especially compared to the previous gen, are a lot lower. So we see 70 to 80 degrees on the P cores while running Cinebench, while the CPU consumes up to 240 watt under load. So that is already a big improvement compared to the previous gen. This CPU is much better when it comes to handling and transferring the heat towards the cooler. I'm running a 360 AIO, by the way. Apart from the P core and E core clocks, as I pointed out earlier, we also have the ring clock. Stock is 3.8, D2D clock stock is 2.1, and NGU clock stock is 2.6 gigahertz. Comparing the 285K in R23 with the other CPUs, we can see that Intel performs quite nice, in multithreading at least. It can even beat the 9950X AMD. In my case, it only beats it by 3% while also consuming 20% more. 42,700 points is what I can get with a 285K with 5 runs averaged, and that was also with the stock Intel power profile. So all the benchmarks I was doing so far were done with the Intel stock power profile that Intel forces the motherboard vendors to use. Getting back to the DLVR and how it helps the CPU, especially in the low and mid-load scenarios. So for example, gaming where it consumes maybe 70 to 100 watt under load. That might also be cases where not all of the cores are loaded identically, or like a game that only loads 1 or 2 cores, where you can have a high core boost. So you have 2 cores that are boosting maybe a little bit higher, because the DLVR allows each single P core to get an individual voltage. So it means that one core is boosting high, only this one core is getting the high voltage and the other cores are getting a lower voltage. The E cores are fed by cluster, so 4 E cores are getting 1 voltage. So it's just much more precise when it comes to the power delivery, and that is especially for low and mid-range load scenarios very interesting and helps the CPU to become very efficient. The problem with DLVR is the high load scenario, for example running Cinebench R23 as we just did. And that's also the example that I took. So you can see in this example the CPU is taken with a 240 watt, that is exactly what we saw. And we are assuming an input voltage from the VRM to the CPU that could be 1.5 volt. And internally, the CPU would break down this from 1.5 to 1.1 volt. It's a bit easier if you just imagine the DLVR as being a resistor that is cutting down the voltage. The current to the CPU cores, we can assume the current in this example with 220 amps. That is given by the overall CPU power draw of 240 watt and the CPU core voltage of 1.1 volt. That means because of the 0.4 volt drop on the DLVR, we are generating 88 watt of power loss through the DLVR. It is a very simplified example, but it's roughly what is happening in the CPU. So if you run Cinebench R23 and you see an overall power consumption of the CPU of 240 watt, only about 170 watt are necessary for the calculation itself, and the other, let's say 70 to 80 watt, are just the power loss on the power delivery of the CPU, the internal DLVR. And that's especially the problem with the very high load, and is much less of a problem in the gaming scenario. That's why we do this very simplified calculation again for the gaming scenario. We are estimating 80 watt under load, which I think is realistic. And we are using again an input voltage of 1.5 volt, which should also be realistic. And you might see in the gaming that the CPU is getting a slightly higher voltage on the P cores, for example, because they can also boost higher. So we assume 1.2 volt on the P cores, which is just higher voltage, so a lower voltage drop of only 0.3 volt. And also a lower current. In this case, we assume 67 amps. And that gives us an overall loss on the DLVR of only 20 watt. So in a lower case scenario, this is like a quarter of what's happening in Cinebench. And there you see that in gaming, this is much less of a problem because of the lower power consumption, because it's only about 20 watt maybe that you have power loss over the DLVR, while you have the benefits. You know, you can have the more precise, more accurate voltage towards the individual cores. So not all the cores are constantly getting fed the same high voltage, which is the result why the 285K is very efficient in gaming, but it's also the result while if you look at Cinebench R23, the 285K was suddenly worse than the 9950X, while the 285K beat the 9950X in gaming. And that's just because of the power loss of the DLVR. A few days ago, I saw a video from Jay's 2 cents where he was talking about the DLVR and that there is also something called DLVR bypass mode, or ASUS calls it the power gate mode. And as the name implies, it's bypassing the DLVR. So what you have currently is that you have the input voltage, DLVR, and then the CPU core voltage. And with this bypass mode, you can bypass the DLVR and use the input voltage as a core voltage. That means you no longer have the possibility to have individual core voltages, but you also get rid of the overall power loss of the DLVR, which, depending on your scenario, like a high load scenario, is extremely beneficial. And I would say it would be extremely stupid from Intel's side to get rid of this. And that's also why I didn't really understand why Jay wanted Intel to do this like right now and like earlier the better. Yeah, I'm not sure why that is, but let's just go to BIOS. Before we go into BIOS, just a quick recap of stock condition. We see about 230 to 240 watt under load in R23. If you want to track the real core voltage with ASUS at least, you scroll down to ASUS EC and they are reading P-Core 7 DLVR, and that is the real core voltage that's sitting on P-Core 7. But in Cinebench R23, all the cores are roughly clocking the same clock, so you can assume that the P-cores are running somewhere between, as you can see, 1.18, 1.21 volt. And then we have the V out voltage, which I called the input voltage. So that is the voltage that's fed from the motherboard to the CPU. And here we see something between 1.4 and as high as 1.5 volt. In BIOS, I'm basically running a manual OC with bypass mode that is replicating stock. I switched to ASUS Advanced OC profile to disable some power limits, otherwise the CPU might throttle a little bit under load. I applied 54 on the P cores and 56 on the E cores, which is just the stock scenario. So there's no change on the clock. I just raised the power limits, fixed the multiplier, and I changed the CPU DLVR mode, which is typically normally on regulation, to power gate mode. And I changed the voltage, that is normally the input voltage to the CPU, to 1.33, which will then drop under load to our identical core voltage as before. We are now running again Cinebench R23. If we pay attention to the clocks, they are as what we see in the stock condition, 5.4 on the P cores, 4.6 steady on the E cores. If we pay attention to the temperatures, they are about 5 degrees Celsius less than in the stock condition. I'm just starting Cinebench over again. And we are paying attention to the CPU package power, which is suddenly reporting 270 watt. You might now think, wait a minute, you just told us that with power gate mode it should consume less power. It's true, but hardware info in power gate mode is reporting a wrong package power draw. And that is because this seems to not really measure it, but rather calculate it over the VID, which doesn't align anymore with how the CPU would normally request the voltage right now. And that's also how I found out about all of this, because if you see that now hardware info reports 270 watt power draw, while my CPU stays colder by 5 degrees Celsius, that doesn't make a lot of sense. If it would increase 30 watt in power, it should also be 5 degrees Celsius colder, but it's the opposite. In power gate mode, it is highly recommended that you go down here, at least if you use an ASUS motherboard, you can check the VRM vCore power. And that is what the motherboard measures. So that is the real power that is currently delivered from the VRM to the CPU. And here we can see it is only between 175 to 185 watt. I'm just running Cinebench R23 again. This is just to compare now the bypass mode, because we will shortly switch back to stock condition. And here we see 43,200 points. So we just revert back to optimized defaults. And all we're doing is load XMP profile. Back in the stock condition, as you can see, temperature is again slightly higher. We can see, however, a lower CPU package power draw, again between 230 and 240 watt. But now, if we scroll back down to the VRM vCore P out, it tells us also about 230 to 240 watt, which just correlates in the stock condition with what you see with the CPU package power draw up here. So in stock it makes sense. But there you see there is a difference between the bypass mode and why the CPU package power draw is just reported wrong in the bypass mode, and you have to rely on the VRM vCore P out in that case. As I told you, Jay pointed out in his video that he wants Intel to get rid of this feature ASAP, and it should have already been removed now. I'm not sure what his intention is, why he thinks it should be removed straight away. It's actually an amazing feature, and what I showed you is something that can be very beneficial if you run high multi-threading loads like Cinebench, or you're doing some rendering all the time. Then it might make sense to use the power gate mode and just adjust your voltages a little bit, and this way you will be able to just draw a lot less power. So as in my example, going down from 240 watt to 160 watt, and also having lower temperatures, which means that you have a lot more headroom for overclocking. So with this headroom, you can just easily increase the voltage a little bit further and get more clock out of the CPU once you run multi-threading load. So at least from my opinion, the bypass mode or power gate mode for multi-threading and overclocking is pretty amazing. I also personally talked to Intel about this topic before, already a month ago roughly, when I was visiting ASUS in Taiwan for the overclocking event, and already there they expressed that they want to disable the power gate or DLVR bypass mode. I'm not sure why, they seemed to be very concerned. I don't really understand why that's the case, because it's a pure overclocking option. And I mean, what's the difference from just in the normal mode raising your voltage to 1.5 volt all day? I mean, the normal average user would not use this from my perspective. You can be happy if the average user finds his way to the XMP profile. So how likely is it that he digs all the way down to the bypass mode? I'm not sure about that. So I don't really understand why Jay wanted Intel to also get rid of this. Doesn't make a lot of sense to me. But even if they do so, I already spent a lot of time testing how we can bypass the disabled bypass mode. We can't really, but what the bypass mode does is just running through the DLVR, which is something we can artificially do as well, in the way of lowering the input voltage and increasing the V-core. So on Arrow Lake, it is possible to save power by increasing the V-core because you will reduce the voltage drop across the DLVR, and thus you just reduce the overall power loss on the DLVR. Again, back to BIOS, ASUS Advanced OC Profile to get rid of most of the power limits. Manual clock P-core is 5.4, E-core is 4.6. And if we go all the way down to the voltages, the only thing that we changed is now getting regulation mode on the DLVR. The performance core voltage is set to 1.28 and the VRM core input voltage lowered to 1.38. Again, checking with Cinebench, first of all, always make sure that the clocks are stable, which is the case. The temperatures are again slightly lower than stock. And again, the CPU package power is reported wrong. As you can see, I mean, it's higher than stock and the temperatures are lower. So that would always be the sign for you that it really doesn't make a lot of sense. So we scroll again down to ASUS EC. We see that P-core voltage is slightly higher than stock. Stock was 1.18, now we are at 1.22. So that's slightly increased. We decreased the input voltage, and this allows us to now only have 190 to about 200 watt under load, whereas with stock we saw about 220 to 230. So I would say that's like a 10 to 15 watt decrease by simply increasing the V-core and decreasing the input voltage. This is also what I have been enjoying the last weeks with Arrow Lake. I saw that some people are disappointed with the platform, but from a technical perspective, this is a lot of fun. There's so much you can tweak with this platform. And there were also a lot of discussions about what affects the CPU to perform worse in some of the gaming scenarios. And I saw discussions that the ring clock might be part of it because the CPU is made from the different tiles. We have the compute tile and then it's connected to the SoC tile. So the connection in between is the D2D clock. So we no longer have only ring clock, we also have D2D clock and the NGU clock. NGU clock is inside the SoC tile. So there's a lot of things you can try, a lot of things you can tweak and play with. And I also wanted to try these things and see how this affects gaming. So I spent a lot of time also testing gaming with increased ring clock, increased D2D clock, and also increased NGU clock to see if this helps minimizing the performance penalty that we're seeing in some scenarios. I then clocked the CPU manually to 4.2 on the ring, D2D to 3.8 G, and NGU to 3.6 GHz. That was the maximum that my CPU could stable do with the stock voltages. With these settings, I again tested Counter-Strike 2 and Assassin's Creed, mainly Counter-Strike 2 because this was the scenario for me where the 285K just performed the worst, and Assassin's Creed because there it performed the best, to see what the differences are. The ring clock alone already helps quite a bit in Counter-Strike 2 to at least increase the average FPS. In my case, from 710 to 760 FPS. So that is a performance increase of 7%. Increasing the D2D frequency, so the connection between the CPU compute unit and the SoC tile, helped only to increase additional 20 FPS on average and a 13 in the 1% low. Increasing NGU clock didn't really help anything. This short part will be a spoiler about one of the upcoming videos with direct die cooling for the 285K because you can push it quite a lot and it helps to get performance, but it would be too much to cover this also in this video, so just a quick side. I was able to push my CPU to 5.7 GHz across the P-cores, which helped to increase the average FPS to be the strongest CPU in my Counter-Strike 2 scenario. However, that was just for average, because if you look again at 1% low FPS, it's still quite far behind the 14900KS and the 7800X 3D, so that really didn't help for the 1% low, and I'm not sure why. The behavior in Assassin's Creed Mirage was quite similar. Increasing the ring only helped to increase the performance by about 5%. Increasing D2D and NGU didn't really help at all. But in this scenario, direct die and massive overclocking actually helped to push the 285K past the 14900KS. 2% more performance, but 30% more power draw. Not as bad as I expected, but unfortunately this is one of the only scenarios where I saw the 285K actually beating the 14900KS. Time for the conclusion finally. It's probably going to be complex and long, same as my testing and same as the platform itself. I think it is a right step in the right direction. Generally, if you look at the CPU, it consumes half the power, it's running a lot colder. That is something we would have needed already for 14th gen. I wish that this CPU was out for 14th gen, because now it has to compete kind of with itself, like with the 14900K and a KS, which are those like far pushed CPUs, high clocked, high power consumption, and thus also high performance in a lot of scenarios, which the 285K just can't get in a lot of scenarios. That's why it's often behind. Intel 1851 as a platform, as a socket, is still interesting because it has a lot of features to offer. We have PCIe Gen 5 for the GPU natively, we have one M.2 slot natively with Gen 5, we have an additional native 4.0 slot, and most of the motherboards come with a lot of other M.2 connections, so you can probably build a nice workstation with it, and the CPUs are probably also good for like light and mid workloads because it's very efficient. But when it comes to gaming, you have to keep in mind that there is still the 7800X 3D. And this is probably what we already expected when we saw the initial launch slides from Intel, where they didn't mention the 7800X 3D with a single word. And that's because they are far behind the 7800X 3D. And now we have to keep in mind that the 9800X 3D is probably around the corner and will be even faster. So gaming-wise, that is a big problem for the 285K. The entire DLVR topic is interesting because it's, the DLVR helps in the gaming scenario where the CPU is bad, and it harms the CPU in the workstation scenario where the CPU is good. So that is kind of weird. If it didn't have the DLVR and it would just feed a lot of voltage to the P cores and E cores during an all-core load, then it might be even better than the 9950X by far. But yeah, that is just very interesting how the CPU is technically designed. In gaming, as expected, AMD is just much stronger, as I said, especially with the 9800X 3D around the corner. But I still think I'm not disappointed by the platform. I think it is a great step in the right direction, moving away from this high power draw, high temperature. I think it's actually not bad. I hope you enjoyed this video. Thanks for tuning in. See you next time. Bye bye.